Hello everyone, I am Magpantay with my groupmates Calingasan and Gragasin. Today, we will be discussing about fast Fourier transform. But before that, let's define what Fourier transform is. Fourier transform, according to what we have researched, is one of the most important techniques in data analysis. It is one of the most important algorithms ever developed, especially for computations with computers. Fourier transform is extremely important for audio compression, image compression, signal processing, and many more. It is a central algorithm for all data analysis and data compression. Basically, Fourier transform is built on some idea that some functions are better approximated with sine and cosines. In mathematics, Fourier analysis is a field that talks about how to approximate a function with an infinity series of sines and cosines. But what we really are interested with about is that how do we apply Fourier series or Fourier transform on data? And this is where the notion of discrete Fourier transform comes in. So now we're gonna talk about the discrete Fourier transform. So the entire idea here is that how do we take a data and represent that data as the sum of sines and cosines. Let's assume I have a function f over some spatial data of variable x, and I have some interesting function with data sampled in various locations, either on space or time, depending on what x is. And then I'm gonna call this data series as f0, f1, f2, f3, and so on up to fn minus 1. Started from 0, we have an n total measurement of points in this function. What we really would like to do is to take this whole vector f and gonna take this collection of measurement and run it to our discrete Fourier transform, and we're gonna get another vector of n numbers. This is called our Fourier coefficient. This sounds complicated, but it will be more clear later on. So the entire idea is that we can take the function f and write it as a sum of a bunch of functions of sine and cosines. So this a bunch of functions of sine and cosines multiplied by a coefficient will be resulting to the original function f. And those coefficients are our Fourier coefficients. Now, let's talk about on how do we solve DFT or the discrete Fourier transform. So there are different ways on solving the DFT, but in this session, we will be presenting the main computation or the formula for getting the DFT, and we will be focusing more on the DFT matrix. So the formula for getting the DFT for f of n is, so capital F represents the coefficient of Fourier coefficient. So f of k is equals to the summation of n is equals to 0 up to n minus 1 f of n multiplied by w of n raised to nk. So w of n in other reference is also called as omega of n. So omega of n can be written as e raised to negative 2 pi I over 2, which if you're familiar with complex analysis, it will be equal to the cosine of negative 2 pi I over n plus I sine 2 pi over n. So let us try solving DFT for some value of f of n. So let's assume that we have a f of n function which has the elements of 1, 2, 3, and 4. So to get the Fourier coefficients or the f of k, so we need to get the f of 0 times omega n raised to 0 times k. Next, f of 1 times omega of n raised to 1 times k. So next, omega of f of 2, then multiplied by omega raised to 2 times k. And then f of 3 times omega of n raised to 3 times k. So simplifying the equation, it will give us, so 1 times 1, 2 times omega of n raised to k, 3 times omega of n raised to 2 times k, for omega of n raised to 3 times k. So let us solve for f of k. So let's assume k is equal to 0. So by substituting 0 to all the values of k, so we got 1 plus 2 plus 3 plus 4. That will give us f of 0 or capital F of 0. Our coefficient is 10. So basically, we can get the nth frequency using the omega of n as a complex number. And what we really want is a matrix where if we stack all our data in F into a vector of F0, F1, F2, F3 up to Fn minus 1 and multiply it to our DFT matrix, so we will get a vector for our Fourier coefficient. So doing this process or computation n times will result to O of n squared. So basically, discrete Fourier transform has a complexity of O of n squared, which is kind of slow for a big or a huge data input. So with this, we will be presenting to you the fast Fourier transform, which lessens the time of the complexity of DFT.
So I will try to explain how the fast Fourier transform works, or give an idea of how it works. So the fast Fourier transform is a fast computational algorithm for the discrete Fourier transform. It is a divide and conquer approach for implementing DFT. So I will be discussing the divide, the conquer, and the combined parts of the divide and conquer approach for DFT. So let's call our problem. So our problem is, at this in my iteration is, we want to transform this vector into this vector. So in my case, this is a vector of coefficient, and this is the y values for a given polynomial. So set of polynomials, I mean. So our goal is to find the y values here. So this can be done by inputting the x values here into our coefficient and then getting the y values for each y member. So this can be done easily by multiplying the x values here against the column here, a coefficient, and then we will get the y0. So then repeat this until we get all y's for this sample. Okay, so our goal is to find ax for all x in the element set of x here. So the way that I described a while ago can easily be done programmatically. Unfortunately, it can only be done in n squared time. So we want to do something better. So first, we divide ax into two equations of even coefficients and odd coefficients. So most of the time when we divide vectors, we divide it in half, in the left part and the right part. But this time we will try a different approach. We will divide it into the even coefficients and the odd coefficients. So a even x would be defined by the summation of a 2k multiplied to the x raised to k for all x is equal to 0 up to for all k is equal to 0 until k is equal to n over 2. So a 2k would just be the even coefficients here, and this will be done also for odd, except instead of 2k we would use 2k plus 1, and then we get the resulting vectors from here and here, and then combine them, and then we will get our a of x. So we will input the value for a even x squared, so that x to the k would be 0, 2, 4, 6, and 8 here. 0, 2, 4, 6, and 8. And do the same for odd. except for add, we multiply an additional x here. So instead of 0, 2, 4, 6, 8, we would get 1, 3, 5, 7, like 1, 3, 5, 7, so on and so forth. So meron na tayong divide and conquer na, divide and yung combine. So now we get to the rather tricky part, the conquer part. So we recursively compute a even y and a add y for y is an element of x squared such that x is an element of the set x. However, this is still of n squared. Kasi yung x natin, hindi siya bumababa. Parang dito nababawasan lang sa atin is yung n lang every time na pinapasok natin. Pero yung x squared pa rin siya natin pinapasa. Next, kunyari, a even x squared. After nito, a even x squared ulit siya. So, iti-test pa rin natin siya sa all ng values dito. I-compute pa rin natin yung x squared. So, for example, kunyari yung 2, 3, 4, 5. Pag in-square kasi natin siya, 4, 9, 16, 25. So, kung 4 ka nagsimula, 4 pa rin yung ending mo. And then, we want that. Gusto nating tignan kung pwede ba natin siyang pababain. Gusto natin na itong x na to maging katulad itong n over 2. Bumababa din by half. So, what we want is collapsing. So, we want the cardinality of x squared be just equal to x over 2. And then x squared is collapsing or x is equal to 1. Cardinality of x is equal to 1. So, ano ba yung ibig sabihin nun? So, ang gusto kasi natin, pag in-square natin yung isang number, parang, pag in-square natin mga numbers, yung set natin ng numbers, makalahati na lang dapat after natin square. So, pwede naman talaga yun. So, for example, we want a set of x with the cardinality of 1. Pwede natin siyang i-define as 1. So, yan na yun. Pag in-square natin siya, 1 pa rin. Paano pag ang gusto ko ay set of x with cardinality 2, pero after niyang i-square, maging 1 na lang siya. So, try yung mag-isip. So, tingin ko madali na naman natin maisip na mag-assign lang tayo mamili lang tayo ng same na positive and negative na number. So, for this, we chose negative 1 and 1. So, pag i-square natin si negative 1, 1 yung sagot. Pag i-square natin si 1, 1 din yung sagot. So, yung cardinality ng x squared natin dito, from 2, naging 1 na lang. Gets nyo? Okay. So, another example. So, cardinality of set of x with cardinality 4, na pag in-x squared natin, na maging cardinality na lang ay 2. So, pwede tayo mag 1, negative 1, I, and negative I. So, ayun. Parang gano'n din sa kanina, ang square nito ay 1 and ang square nito ay 2. Pwede din natin extend ito hanggang sa cardinality of 8. Magkakaroon lang tayo ng complex na numbers katulad ng I. So, yun nga, technically, lahat ng mga complex numbers, meron tayong 2 roots lagi for a particular square. Yung positive niya at yung negative niya. So, si 4, meron siyang positive, negative 2. Si 9, meron siyang positive, negative 3. So, si 1, yun, may positive, negative 1 siya. Yun. So, i-exploit lang natin tong part na, yung property na yun ng mga squares and roots, okay? And then, sa 8, meron tayong 1, negative 1, I, negative square root of 2 over 2, I minus 1. Square root of 2 over 2 times I minus 1. Negative square root 2 over 2 times I plus 1, tsaka square root of 2 over 2 times I plus 1. So, madali itong makita as, so, sa complex plane natin ngayon, meron tayo, yung x-axis natin is yung real part, and yung y-axis natin is yung imaginary part nung number natin. So to illustrate this, let's take for example this number 1. So meron tayong 1 na value for our real part. Tapos kaya siya nandito sa mismong line na to dahil 0 naman yung value niya ng imaginary part. Tapos ganoon din dito, parang ganoon din dito sa I. Sa I meron siyang 1 na value for imaginary part and then 0 na value for the real part. Now, kunyari, tignan naman natin itong square root of 2 over 2i plus 1. Meron siyang square root of 2 over 2 na value for the imaginary part and then square root of 2 over 2 na value for the real part. So, ganun lang to. Ganun lang siya pinaplot dito. So, lahat ng mga numbers natin na roots na pinapakita natin kanina, pwede nating i-plot ngayon dito sa complex plane na to. Tapos pag-introduce pala ako ng bagong letter, CW, WN. So, N is the number of yung cardinality nitong set natin. So, given that N is a power of 2, pwede daw natin i-divide lang yung circle na to, yung unit circle na to sa N, tapos yung pagkaka-divide natin sa kanya, yung pagkaka-cut natin ng circle, yun na yung different roots ng unity. Unity kasi kung titignan nyo, lahat to ay part lang ng unit circle. Okay? Ang radius nito ay 1, 1, 1, 1, 1, 1, 1, lahat. Okay? So, ayun. So, paano natin na-illustrate yun? So, dito ang N natin ay 8. So, ibig sabihin daw, pag dinivide natin to by 8, yung each na division nun, yun ay yung mga roots niya. So, tignan natin. So, si 1, ito yun. Siya ay si W0 for N8. Si square root of 2 over 2i plus 1, ito siya. Si W1 for N equals 8. And so and forth and so forth. Ito yung next na term dito, dito, hanggang sa umikot siya. So, ano ngayon kung naipa-plot natin siya ng ganito? So, nakakatuwa kasi dito is, aside from na-prove na natin na napapalit talaga natin yung cardinality, is, pag nag-start tayo dito, para malaman natin kung ano yung square niya, i-multiply lang ulit natin siya dito, syempre. Ang ibig sabihin nun dito ay mag-move lang ulit tayo ng kung ilan yung part niya dito. So, kunyari may 1 na part dito. So, para ma-square natin siya, ito lang yun. Okay? So, dahil n over 8 to, n over 4, ito yun. I. So, tama naman. Ang square ng square root of 2 over 2i plus 1 ay I. So, di kininiwala siguro kasi masyadong complex. So, tignan natin dito. So, I, pag yung I naman, so n over 4 siya. So, pag noble natin siya, naging n over 2, ito siya. Negative 1. So, tama diba? I is defined as the square root of negative 1. Tapos, ganun din dito. Ang square nito ay n over 2 to, so ang square na to ay n, so babalik tayo sa 1. Okay? So, ganun din. And another fun part is, di ba nga, by pair silang lahat. So, alam natin na yung n compare nito ay ito, at ito. So, isa sila ng mga squares nila. So, tignan nga natin. So, dito ang square nito ay ito. So, assume din dapat ito din, yung opposite niya, yung compare niya, ang square niya din dapat ay ito. So, 1, 2, 3, 4, 5. So, dito ay 1, 2, 3, 4, 5. Tapos yun. Ang galing lang din. Parang, nga no. So, talagang yung square nito is yung doble lang nung distance niya dito, nung angle niya. Okay? So, iti-take advantage lang natin yung mga yon para mapalit natin yung cardinality ng x squared. So, gamit yung mga daya na yon, yung mga tricks na yon, um, yung t of n natin dito, t of n over 2, tn over 2, cardinality of x, pwedeng maging tn over 2 na lang siya kasi x natin is nag-half din naman. So, kasabay niyang bumababa yung n over 2. So, gamit yon. So, ngayon, i-discuss natin yung mismong algorithm niya. So, this is the recursive na algorithm galing dun sa book na Introduction to Algorithms. So, ang input niya ay sum vector A, tapos dapat ang length dapat niya, ipapasok natin yung length niya kay n. So, kasi dapat diba si n ay power of 2. So, pag hindi siya power of 2, nadali na lang naman na yung gawin ng paraan para maging power of 2 yung length ni A. Pwede mag-pad tayo ng zeros or mirroring. Pero pinakamadali na siguro for us yung pad ng zeros for this part. So, syempre, yung base case natin, if n equals 1, return lang natin yung value ni A. So, after nun, lagyan na natin ng value si W. So, ito yung sinasabi sa inyo, e to the 2 pi I over n. Bale, ang ginagawa lang niyan ay, kinukuha niya yung value nito. So, kunyari kung 8, ito yung kinukuha niya. Okay? Itong first part. Basta lagi yung first angle yung kinukuha nitong W na to. Wn. And then, W is equal to 1. So, identity lang. And then, dito natin kinukuha yung pinaghati yung A natin. Dito natin nilalagay yung even and then dito natin nilalagay yung odd. 0 yung even kasi 0 daw yung ending ng mga indexes nila. And dito naman ay 1 yung ending ng mga indexes nila in binary. And then we apply recursive FFT for the even, then recursive FFT for the odd. Okay. So dito na mismo yung paglalagay natin ng values dun sa y. So yung pagpasama natin ng mga values nila. So yk is equal to yk 0 plus wyk 1. Bale yung even value ng y na yun plus yung odd value ng y na yun multiplied by w. So, dalawa yung ginagawa natin dito kasi isa lang naman yung square nung sa etong n over 2, k plus n over 2 na to is yung parang dito. N over 2 kasi yung opposite side lang lagi. So, etong n over 2 nyo ito, n over 2 nyo ito. So, alam natin na isa lang naman yung square nila. Okay? So, dito, yung plus na form niya, dito yung plus na form niya and dito yung minus na form niya. And then, i-multiply ulit natin si W sa Wn. Ang mangyari nun is magmula dito, gagalaw siya dito. Okay? Tapos pag nandito na siya, gagalaw ulit siya dito. So, madadaanan natin lahat ng roots of unity. So, and then return y is assumed to be a column vector. Then, paulit-ulit lang to hanggang sa matapos yung buong recursive algorithm ng FFT.
For this part of the presentation, I will be discussing some of the applications of the fast Fourier transform to better appreciate the algorithm. Now, some algorithms had already been derived as early as 1805, but the basic ideas were only popularized in 1965, such as the Kulituki algorithm. Now, the fast Fourier transform was even quoted as the most important numerical algorithm for our lifetime and was included in the top 10 algorithms of the 20th century. The fast Fourier transforms are actually widely used in many applications for engineering, science, and mathematics. Nowadays, it is one of the most indispensable algorithms in digital signal processing. Now, the FFT was actually derived due to the fact that the DFT was considered to be slow with a runtime of n squared, while the fast Fourier transform can come up with runtimes of n log n. Now, before I proceed with an example of the capabilities and uses of the fast Fourier transform algorithm, I would like to discuss briefly a visual representation of the discrete Fourier transform algorithm. Now, given this circle over here with radius 1, Euler's formula tells us that if you take E and raise it to some number and multiply that number by I, you'll actually land on the point you get if you were to traverse that number of units around the circle with radius 1, such as this. Now, if you wanted to consider rotating in the circle at a rate based on frequency and time, you could take the expression and add the said variables, such as this. Now, since the circle is considered to have a radius 1, 2 pi actually describes the full length of its circumference. Now, for example, if the frequency was 1/5, then this vector makes a full turn every 5 seconds to make the equation look like e raised to the 2 pi I. Now, since the convention in the context of Fourier transforms is to think about rotating in the clockwise direction, we simply add a negative to the expression. Now, let's take some function describing a signal intensity versus time, like this one, and let's call this function g of t. Now take note that this function is what we will be transforming from the original domain, which is this one, into the frequency domain using the discrete Fourier transform. Now, if you multiply this function to the current expression right here, like so, it would actually mean that the rotating complex number earlier that is now being scaled up and down depending on the peaks and valleys of the sine wave, like so. Now, the thing that we actually want to do with this wound-up graph is to track its center of mass. One way to do it is to sample different points in time from the original function, like so, and see where they wind up on the wound-up graph, like so. Now, of course, if you sample more points in time that are close to each other, the results are bound to be more accurate. And the formula for that would look like this. But rather than looking at the sum of multiple points and getting their averages, you can actually take an integral of this function divided by the size of the time interval that we're sampling, like so. Now technically what we'd be doing is we'd be choosing a time interval and simply sampling everything within that time interval, giving more accurate results. Now basically this entire current expression right here is just the center of mass of this graph. Now there is actually just one final but simple tweak to be made in this formula. Basically, just don't divide by the time interval, and you will get the actual Fourier transform, which is this one. This would simply show that if a frequency persists for a long period of time, the magnitude of the Fourier transform at that frequency is scaled up more and more, making it more prominent in the frequency domain, like so. Now this graph over here is actually the frequency domain that came from the original domain, which is this graph over here, or rather this sinusoidal wave over here. Now this is more formally known as g of hat of f. With that being explained, we could actually proceed to the uses of the fast Fourier transform. Now take note, the fast Fourier transform is simply an improved version of the discrete Fourier transform in terms of time complexity. Now as for the uses, a prime example would be decomposing frequencies from sound. FFT helps untangle signals, and it also converts signals from its original domain, often time or space, to representation in the frequency domain and vice versa, which was shown in the previous graph. Just to reiterate, this would be the original domain, and this would be the frequency domain. Now, a little info about frequencies. a microphone recording actually just picks up the air pressure, which simply oscillates up and down around its usual equilibrium. Take this graph, for example. Now, this is actually just a pure sound, and the air pressure, as a function of time, it would oscillate up and down around its usual equilibrium like this. Now, given the formula, we could actually compute for the frequency domain, which is this one. Now, in mathematics, there's actually a rule wherein every signal can be thought of as the sum of multiple sine waves. This graph over here actually shows a sine wave that is the sum of two different signals. An example of this occurrence is actually if you just think about two different sounds being played at the same time. And if you apply the Fourier transform into this graph, you would actually come up with this frequency domain. Now take note here that in this frequency domain, there are two peaks being shown in the graph. This clearly shows that there are two main frequencies being played from this sinusoidal wave up here. Now this actually puts decomposing into perspective, because if, let's say for example, the original frequencies are this one and this one, when added together, they would actually form the graph up here. Now, take a look over here. If the first original domain of the frequency was converted into its frequency domain over here, it would show this graph. Now, if the other sound by itself, played by itself, was converted into its frequency domain, it would turn into this graph right here. But then, if you actually add the two sounds and see the resulting frequency, and then convert this graph into the resulting frequency domain using the Fourier transform, you could see clearly that they're simply the sum of the original frequency domains added up together, showing that there are two main frequencies being played in this sinusoidal wave or this sound. Now, actually, if you simply want to decompose some sounds, or if you want to simply flatten out or cancel out a specific sound, let's say for example you want to remove this from the original sound recording, all you'd actually have to do is to flatten out this from the frequency domain, and you'll simply come up with a cleaner sound without this one over here. In a specific sense, for this graph right here, flattening this out would simply end up giving you this frequency right here. So I hope that helps everyone understand and appreciate further the fast Fourier transform. Thank you for listening.